Lesson 7, Nuclear Fission and Fusion. There is no more haunting words than that of Robert Oppenheimer upon watching the world's first nuclear bomb explode. He quoted Hindu scripture, "I have become death, destroyer of worlds." He reported that upon watching it, a few people laughed, a few people cried, but most were silent, and the world was never going to be the same again. The human race has been defined by us trying to find a bigger stick to hit the next person. Wars have been fought over land, over resources. No other animal kills its own species as much as humans. And in our search for the biggest stick of all, in the mid-40s, we came across the nuclear bomb. And it haunted Robert Oppenheimer for the rest of his life. He died in the mid-60s. He was never the same. And it was his work that helped pave the way for this. It also haunted Albert Einstein, who wrote a letter urging to end World War II quickly by developing the nuclear bomb, but upon seeing its destruction that it caused, again was haunted by what scientists had created. So, with this comes great responsibility if you become a scientist. You will create things, and it's down to the rest of the humans what they decide to do with them. Nuclear power powers about 20% of our national grid. You're using a bit of that electricity generated by it now. However, the potential to wipe out all humans on this planet is pretty high. So let's look about what the science tells us, and we'll go from there. So we'll start off with nuclear fission. It was the first one discovered. So nuclear fission. And it started with the idea that what if you hit an atom with neutrons? So we had ourselves a neutron emitter. Off was coming neutrons like so. Created a neutron gun. And we decided to hit a block of uranium. What would happen to the uranium? And what we discovered is that we could fission. Fission means to split. So if I drew the atom like so, what we could do is that extra neutron would tip the balance to split the nucleus into two smaller daughter nuclei. So there they go. So it splits into its two daughter nuclei. And in doing so, it releases huge amounts of energy that were built up inside the nucleus. I said earlier that the nucleus is several orders of magnitude higher in energy than those in the electrons. And that's a common joke with chemists and physicists, that the chemists mess around with low energy electron shells, and it's the physicists who do the meaty stuff in the middle. But don't tell Mr. Dolan that, because he'll hit me. Anyhow, so we have there our uranium. It's then splitting into two daughters. There. Theirs are supposed to be nuclei, but I've given up trying to draw them right. And huge amounts of energy. And if that was it, then we wouldn't have a nuclear bomb. It turns out something quite fortuitous or bad happens. You also get 2 or 3 extra neutrons being emitted. And it's these neutrons that go off and they hit other uraniums. And so what we get is called a chain reaction. And we can draw it like this. If we draw the first uranium, we can show just the neutrons now. So the neutrons will come off. I don't want to be straight on that. I want to be diagonal. There we go. The neutrons come off and they hit other uraniums. And this ends up looking like a probability tree, because now you've gone from 2 to 4 quite quickly. And it's exponential growth. So now we've gone 2 to 4. We then hit more uraniums. We'll go over there. Hit more uraniums. And so we are fissioning over and over and over again. And every time it fissions, it releases 2 more, or 3 sometimes. And now we're at 8. 1, 2, 3, 4, 5, 6, 7, 8. And we call this a chain reaction. And that's what they managed in 1943, 44. If you're doing history, you probably learnt about Little Boy and Big Man. I think it's what they're called. And the idea is all around controlling these neutrons that are released at the beginning to get the chain reaction to take, bit like fanning a fire. You get it just right, the fire will take. Same is true with nuclear fission. So the energy comes. Now, where did this energy come from? Well, Einstein had been doing work and he came up with the famous equation E equals mc squared. E stood for energy. That was easy enough. M stood for mass. And C was the speed of light. And so what he was actually saying is that that energy and mass are related to each other through the square of the speed of light. Now, the speed of light is 3 times 10 to the power of 8. So if you were to square that number, you would get 9, 3 times 3, times 10 to the power of 16. You double the 8. That is a huge amount of energy. So if we took a kilogram of matter and we converted it entirely into energy, we would get, now let's put this into something you might understand, 1,000,000 is 10 to the 6. So 1,000,000,000 is 10 to the 12. And we've got 4 orders of magnitude higher than that. So we have 10,000 times 1,000,000 times 1,000,000 would then get us to 10 to the 16. It is a crazy amount of energy. And when scientists realised this, they thought 2 things. Aha, we can harness the energy and create a wonderful future, and we can create bombs. So the difference really between a nuclear bomb and a nuclear reactor is the control. That if you have control of the chain reaction, then you get a power station. And the first ones went online in the 50s. So you control those neutrons and that stops it from running away. If you have uncontrolled chain reaction, then you have a bomb. So the difference really between the two, and it's the same with the engine in your car. Your car just wants to totally rip itself to pieces. And it's the control of the amount of petrol and the control of the amount of oxygen going to that fire in the piston that's holding the whole thing together. So it's a very fine line between control and uncontrolled, and the destructions that it gives. Just realise it looks like a tree. It's not. It's bombs. Now it looks even worse, like a tree. Damn. The other thing, where is this energy coming from then? So let's look at it. If we looked at it like a chemical reaction, if we took the uranium and we took the little neutron that hit it and we weighed it and we took its mass, like so. If we then carried out the fission, remember fission means to split, we carried out the fission and we measured the products, so we had daughter 1, I'll put D, daughter 2, and we had the neutrons. Well, a funny thing happens. It weighs less. It has less mass. And through Einstein's equation at the top there, I'll grab it and bring it down. Through the equation here, that little bit of mass that you have lost, the lost mass, there it is, it gets turned into energy. And that's where that energy came from earlier, that's irradiated. So you only need a small amount. You only need grams of this to be lost. And then you have more energy than 1,000,000 tons of, 10,000 tons of TNT. So a typical nuclear bomb may only have the equivalent of like 0.5 kilogram of uranium, and that's enough to flatten an entire city. So that's nuclear fission. I think I've covered everything. The other one is far more interesting, and this could be a huge game changer. There was always a question, and it was about the sun. We weighed the sun. We figured out how big it was. We then did geology, and we realised that the Earth was 4.5 billion years old. But when we looked at the sun, 150 years ago, 200 years ago, and we looked at gases, then the sun couldn't be more than a few thousands of years old. Because at the rate it was giving off energy, chemical burning just wasn't really going to be enough. And that really puzzled us. how could we have an Earth that was clearly very old, yet a sun that if it was a burning hot ball of gas, methane or butane, how was it able to live for so long? And it turns out it wasn't that at all. It was all about nuclear fusion. So let's have a hop inside a star a minute. Let's load it up. Hopefully this should work. Come on. We'll hop inside our own sun. Let's go home. Milky Way galaxy. Got all this effort just to get home. And we'll hop to our local stars. And we'll find Sol, part of the solar system. We'll hop in. Zoop. And we're going to plunge towards the sun. And here we go. Are we going to go there now? Thank you. There's the sun. It is a giant ball of nuclear fusion. And let's go inside. So, stars are made of hydrogen and helium mostly. The pressure inside here is such that it is fusing hydrogen nuclei together. So take a hydrogen with one proton, and it needs to be an isotope. So one proton with a neutron. It's buzzing around. The electrons cannot bond. These atoms are too energetic. So we have what's called a plasma. And the pressure and the temperature is so great, about 15 million degrees, that it is literally clicking together protons to make helium. And that is nuclear fusion in a nutshell. So if we skip back, we can see that nuclear fusion, this is when nuclei of isotopes are fused together. Now the requirements, like I said earlier, it happens in the core. You need huge amounts of pressure. So you have the weight of the whole star pushing down on the gas in the centre. And you also have huge temperatures, so 15 mega degrees Celsius. We can actually create this on the planet Earth. We can get temperatures much, much higher. We can go up to 150 million because we can't make as much pressure as the sun. That is crazy big. But we can compensate by having the temperature there. So it requires high temperatures and pressure. And that's been the major barrier to humans carrying this out and using it properly. We'll talk about that in a minute. So what's going on in terms of the reaction? Let's take a hydrogen isotope, and we can take, say, tritium 3,1, add it on to hydrogen 2,1, deuterium, and we can fuse them together. And what we're going to end up with is helium 2, that makes it helium, number 2, 4, and we get given off another neutron. And it's this other neutron that goes and bonds with another nuclei to create more hydrogen 2 and hydrogen 3. So you do need these isotopes at the beginning. Isotopes. You need those isotopes to be fused together to make it. And just like in nuclear fission, if we take the weight of these, so we find the mass, and we find the mass of the products, guess what? It weighs less. Less mass. So where has it gone? It's gone off as heat again. And this time it's an order of magnitude greater. So we end up with heat energy being given off. So the first nuclear atomic bomb we blew up was a fission bomb. It was uranium fissioning. But the second one was actually a hydrogen bomb, with no more hydrogen that you'd find in a party balloon, but it was squeezed right down into a small pellet. And what they did is they created a layering system. So here they had TNT, dynamite. Then they had a layer of uranium, and in the middle they had the hydrogen. So they exploded the TNT, which pressed the uranium. The uranium compressed to create nuclear fission, which then pressed on the hydrogen to create nuclear fusion. So they basically created a small star in a bomb, which I find remarkable. Humans are so clever, but so dumb with what we do with it. So that's nuclear fusion. Now, the hope is that this is going to sort the entire human race out. Whenever you look at science fiction, where it's a utopia, Star Trek, for example, there's unlimited energy and nobody goes hungry, because with that energy you can create crops easily, you can power your vehicles, but more importantly, no pollution. So there is a jet fusion. There is a place in Oxford called the Joint European Torus. This is it. And this replicates a star on Earth. It gets to temperatures of hundreds of millions of degrees, and it holds the gas in place around by magnets. So all around the edges here are magnetic fields, and it holds them, and it's a bit like trying to run a 100 metres race while holding jelly in your hand. It wobbles everywhere. So we're able to hold this gas at that high temperature and fuse it for about 30 or 40 seconds. And the problem is we need it to carry on indefinitely, because the idea will be to take the heat energy that's given out, turn some of that back into electricity to power it, but siphon off for our own use free, clean electricity. Now, saying that you're going to build a star on the Earth sounds really, really dangerous. However, it's not, because as soon as there's a breach, if that gas accidentally touched the wall, immediately the magnetic field would be lost, the plasma would lose its temperature, and so it's extremely safe. Extremely safe. It cannot blow up, because if anything goes wrong, it just goes out. The other thing is as well, there are no harmful byproducts. There is no harmful pollution. All you get out of it is hydrogen and some neutrons. Now, the neutrons are dangerous, but you shield yourself. So when that nuclear fusion reactor is on, that's concrete all around it and steel. Nobody is inside that room. It's a crazy bit of equipment. Now, this is one of the first in the world to ever do it, and this is old. I think it's about 35 years old. Over in France are just about to complete a £20 million one called ITER. And ITER hopes to be the first one to generate a sustainable amount and show that this is possible. So you could potentially power entire countries on just a couple of these small, well, they'll be relatively big, but you won't need many of them. And it will create free, unlimited electricity. The other thing is, what do you feed it? Well, all you feed it is hydrogen. And where do you get the hydrogen from? Well, we've got loads of that. You get it from water. You just do electrolysis. You just put a plus and a minus in, and you just collect the hydrogen gas from that. You bombard it with the neutrons to make the isotopes, and then you fuse them to make the helium. And in doing so, that could give us a total utopia. So fingers crossed, we might get there. The running joke is that when I was a kid, that nuclear fusion was only 25 years away. And now, a lot later, nuclear fusion is 25 years away. So it's a really long-running joke. But we are persevering with it, and it's worth the effort. Anyhow, notes for this are on page 49. And one more lesson to go.